Hi everyone, this is lesson 613 on special right triangles and trigonometry. So on a previous lesson we talked about special right triangles and this is a reminder of what those were. We talked about 30, 60, 90 and 45, 45, 90 triangles. The general case that we're looking at is this special right triangle 30, 60, 90 where the short leg has a measurement of 1, the long leg has a measurement of square root of 3, and the hypotenuse has a measurement of 2. So this is the base case that we compare all other 30, 60, 90 triangles to. So in the general case, I would say if the short leg is x, then we could easily determine the other two sides. The easiest maybe being that if we double that measurement, it gives us the hypotenuse, and if we multiply the short leg by square root of 3, it gives us the long leg. So this is the general format, x really being the scale factor or zoom factor of the triangle. So the same applies to the 45, 45, 90 triangle, where 1 and 1 would be the two legs, and square root of 2 would be our hypotenuse. All right, so these are could be replaced with letters. So if I change the legs to, let's say, a 4, then this is going to be 4, 4, and 4 root 2. All right, so same pattern works for all 45, 45, 90 triangles. So the common mistake is to confuse the two. So make sure you understand the difference. Always have these as a reference written down near you. Anytime you're dealing with triangles, special right triangles, you want to make sure you have one of these triangles drawn out as a reference. So like today we will be using them to learn a little bit more about this relationship in regards to trig. So what we're going to be looking at today is Pythagorean identity. And so we're going to use a little bit of what we've just learned to explore what that identity is. All right, so let's use our special right triangles to calculate the exact answers for trig ratios. So you'll notice below I have a bunch of sine, cosine, tangent, different angles, sine, cosine, tangent of 30, sine, cosine, tangent of 60, and then a 45. So in previous problems, what we would normally do if we wanted to know what sine of 30 is, we could just put that in a calculator, right? But we want to know exact answers. So exact answers means we don't want a decimal, we don't want to use a calculator. If anything, it's a lot nicer to have an exact answer than an approximated, because approximated involves rounding, which means it's not a complete answer. So exact answers are the best for us. So we could get these answers without using a calculator by using our special right triangle. So I've redrawn these for us, and they're labeled accordingly. And another reminder of our SOHCAHTOA trig ratios that you need to know as well. So let's fill in. We're going to fill in our triangles again. So let me zoom into these for a second. So we have our 30, 60, 90 triangle. In this case, we know AC has a measurement of 1. So this is our short leg. So if this is our short leg, then we want to label our other two legs. So in this case, the measurement of BC would be 2 because it's twice as big. And the measurement of AB would be 1 times the square root of 3. So we'll just put square root of 3. All right, and then the 45, 45, since FD is 1, then that means ED must also be 1, right? Since that's the general rule for 45, 45. And that leaves our hypotenuse EF with square root of 2. All right, now that we know all the measurements, all right, that's a little reminder what those are. What we're going to do is answer all 9 of these. We have sine of 30, cosine of 30, tangent of 30. We'll start with those. These are the first 3. So we're focused on sine of 30. And sine is opposite over hypotenuse. So I'm looking for opposite and hypotenuse. So we're looking at these two sides. So that's going to be a 1 and a 2 for us. All right, so I'm going to put sine of 30 is going to be the same as 1 over 2. All right, so you'll notice no calculator was needed. I already know sine of 30 is going to equal to 1/2. If you actually put that in a calculator, you should notice it's going to give you 0.5, which is 1/2. All right, we didn't need one for this. Cosine of 30, we'll do the same thing. So now I'm still looking at angle 30 in the picture. Cosine is adjacent over hypotenuse. All right, so this is going to be adjacent over hypotenuse. All right, so make sure you definitely know where your opposite, adjacent, and hypotenuse are in the picture. If you need to label that for this, then please go ahead and do. So we will have to change, when we change angles, you most likely will have to change your labels as well. All right, so in this case, cosine of 30, adjacent is square root of 3 over 2. So I'm going to put square root of 3 over 2. And then tangent is going to be opposite over adjacent. So opposite is 1, and adjacent is square root of 3. All right, so we have 1 over the square root of 3. All right, so you'll notice we have exact answers for all 3 of these. We didn't have to use the calculator once. We don't want to have a decimal answer for these. So if you have decimal answers, you're working 10 times harder than you need to. All right, so let's do the same thing for the next 3, the next column. You'll notice they're all have 60 degrees. So that means we don't see a 60 in this picture, but if you look closely, if we know where 30 is, right? If I know where 30 is, then that must mean that the other angle is 60 degrees. All right, so let's focus on sine of 30. So this is where the opposite changes. So opposite is square root of 3, and hypotenuse is still 2. So we're going to have square root of 3 over 2. And then we're going to do cosine of 60. Cosine of 60, so we're looking at adjacent, and hypotenuse. All right, so that's going to be 1 over 2. And then tangent of 60 is going to be square root of 3 over 1. All right. So before we go on to the last 3, what we want to do is kind of see if there's any connections with the numbers we just saw. And so what I notice, sine of 30 is 1/2. That's also cosine of 60. Right? Those are actually the same measurement. And then if we look at cosine of 30, square root of 3 over 2, you'll notice sine of 60 is also square root of 3 over 2. So those have the same answers as well. So that tells us something. Sine of 30 and cosine of 60 are equal to each other, right? Which makes sense. And if you remember, cosine really just means the complement of sine. Complement means they add up to 90 degrees. So look at that. 30 plus 60 gives us 90 degrees. So sine and cosine of complementary angles should equal each other. So you'll notice here, sine of 60, cosine of 30, right? They give us the same measurement. All right, you might also notice on the tangent, we have 1 over square root of 3, and then tangent of 60 ends up being square root of 3 over 1, right? What do we call that when the fraction gets flipped? I want to see if you know the name of that. All right, well, that is what we call reciprocal. Okay, so hopefully you got that correct. Moving on to the last row, we're looking at 45s. So that means we're going to be looking at this second triangle. Sine is going to be 1 over square root of 2. Cosine is going to be also 1 over square root of 2. And tangent of 45 is going to be 1 over 1, which reduces to 1. So you'll notice here as well, if we add 45 and 45, that's 90. Those are complements of each other, and you'll notice that these equal to each other. So let me highlight those for us. So these were the same. All right. So those are just little connections that we need to know. You should have this as a reference because we're going to be reusing these numbers in the next problem. All right. So now that we've kind of practiced a little bit of our 30, 60, 90, 45, 45, you could see how we could use it to answer some questions in trig. So in case you ever have to solve a problem that involves cosine of 60 degrees, you shouldn't have to reach for your calculator to figure out what that is. You should already know it's going to be 1 over 2. That'll never change. Same thing with all these other common angles. So 30, 60, and 45 are going to be common angles that you should have at some point in your math career. You might have some of these memorized. So if it's not in this class, possibly in the next class or beyond. All right, so what we're looking at next is really developing our Pythagorean identity. So we're going to use a little bit of what we just learned and some old knowledge as well. And so let's look at this triangle given to us where it's labeled hypotenuse is 1 in this case, and we have x and y as our two leg measurements. So if I want to know what sine of theta is in this specific triangle, sine is going to be opposite over hypotenuse. So opposite over hypotenuse is going to be y over 1. And then cosine of theta, in this case, cosine of theta is going to be adjacent over hypotenuse. All right? So this is going to be x, let's use a different color, x over 1. All right, well, y divided by 1 or x divided by 1, that could be simplified to something a bit simpler. So technically I could say sine of theta is equal to y, and cosine of theta is equal to x, right? I could eliminate that one. It's not really being used. So that now I know, if I want to know the measurement of y, all I need to do is take sine of theta. So if I know the angle, then I could figure out the side length. Now this only works because this hypotenuse is 1. So this doesn't work for all triangles. It's only because our hypotenuse is 1. All right, so now that we know these two relationships, and since we also know Pythagorean theorem, here's a reminder of that. Leg squared plus leg squared is hypotenuse squared, or sometimes we think of it as a squared plus b squared equals c squared. Since we know that, we could use what we just developed from part A and plug that into our Pythagorean theorem. So let's do that now. So this is going to be sine theta squared, right? That's one of the legs. And we're going to put the other leg, which is cosine theta squared. And our hypotenuse in this case was 1. So this is 1 squared. All right, what this leaves us with, that could be simplified. And so we're left with sine of theta squared plus cosine of theta squared is equal to 1. All right, so this is what we're going to end up calling the Pythagorean identity. All right, and so we're building up to really proving this. So this is what we think is true based off of rewriting these this relationship into little equations, plugging them into a theorem that we already know. And so if this is true, then we want to know, is it true for all angles or is it only true for this triangle? All right, so let's investigate this a little bit further. So let's try out a couple of angles. So you'll notice below I have sine of 30 squared plus cosine of 30 squared. All I'm doing is I'm taking this, and instead of theta, I'm going to plug in some actual angles, right? So that makes more sense. Well, we just calculated these on the previous page of notes that I just went over. So sine of 30 and cosine of 30, we don't want decimals, we want exact answers. So what I'm going to do is I'm going to just go back, sine and cosine of 30. So let me just look, sine of 30, so sine of 30 was 1/2, and then cosine of 30 was square root of 3 over 2. All right, so let's see if I could remember that one. So I'm going to go here, and I'm going to put, okay, so this is sine of 30 is really 1/2. So that's going to be 1/2 squared, because there's still a square there. And square root of 3 over 2 was cosine of 30, and there's still a square there. All right, so let's simplify this and see what this comes out to. 1/2 squared is 1 over 4, right? Because 2 squared is 4. And then square root of 3 squared is 3. And 2 squared is 4. All right, so now if we add 1/4 plus 3/4 is going to give us 4 out of 4, which reduces to 1. All right, so, okay, so this tells us that worked for an angle of 30 degrees, which is what we wanted, right? This is what we thought was going to happen. We said it was supposed to equal to 1, and you'll notice it did equal to 1. All right, so let's try it for the 45. Sine of 45 and cosine of 45. Let me look back at my notes and see what those were. All right, so this is 1 over square root of 2 and 1 over square root of 2. Well, they're both. All right, so let's plug those in. So this is going to be 1 over the square root of 2 squared plus 1 over square root of 2 squared. All right, so if we're going to multiply this out, 1 squared is 1, and then square root of 2 squared is square root of 4, which is 2. All right, so this reduces to 1 over 2, and that means the other one reduces to 1 over 2. And so 1/2 plus 1/2 is 2/2, which equals to 1. All right, you'll notice they both equal to 1. That's exactly what we thought was going to happen. So the question is, that's great. Does it work for all angles? We tried two examples that happen to work. Now, does this only work for special triangles? Now, that could be the case, so we would have to prove it for all angles. All right, so we're going to look at a proof. I think I have this one complete for us, and I'll just explain it as you copy this down. You wouldn't have to recreate this, but you might need to have it in your notes as a reference in case it comes up in some random question. All right, so I'm going to start with a new triangle, triangle ABC. You'll notice I've labeled all the sides as well. And we know the Pythagorean theorem, right? We've talked about that a couple times today. And the general formula that most of us know is a squared plus b squared equals c squared. So that works well with this triangle because A and B are the legs and C is the hypotenuse. All right, so that's what I know is true about this triangle. And what we've just learned a little bit about trig in this lesson was that sine of theta is going to be opposite over hypotenuse, which is A over C. And cosine of theta is going to be adjacent over hypotenuse, which is B over C. So those are two relationships we know. And from the previous problem, what we know, or at least we think is going to work for all triangles, is this relationship here. So sine of theta squared plus cosine of theta squared equals to 1. And so we're going to combine all this together. And since I'm going to replace this sine of theta with this fraction, A over C, and this cosine of theta with this B over C. So you'll notice it over here. So I have A over C squared plus B over C squared. Right? So this has transitioned. We've eliminated the trig and we've replaced it with the fractions instead. All right, so now we have this equation and we could try to rewrite it. And so what I'm going to do is multiply the squares out. So A times A is A squared, C times C is C squared. Same thing with the B's and the C's on the second fraction. And so you'll notice since they have the same denominator, we could combine them into one fraction. And in order to get rid of this C squared on the bottom, we can multiply C squared to both sides. So if I multiply C squared to both sides, this eliminates the C squared on the left side, leaving us with A squared plus B squared. And now we have a C squared on the right. So you'll notice this is the Pythagorean theorem that we saw before. So which means this Pythagorean identity is going to work for all right triangles. So not just the special right triangles, but it's going to work for all right triangles. All right, so in summary, what we proved was that sine of theta squared plus cosine of theta squared equals to 1, right? And this is for all measurements of theta. So I could plug in any number for theta, and whatever I do, it goes into both of these. They're not different angles. So this could be sine of 15 squared plus cosine of 15 squared. And I know for sure, I already know what that's going to equal to. It's going to equal to 1. I don't even have to put it in a calculator. As soon as I see that those angles are the same, and it's a sine and cosine, and they're being squared, then I already know the answer is going to be equal to 1. All right, so this is what we call Pythagorean identity, and we use this really to solve more complicated right triangle problems. You won't use it regularly like we've been using our normal trig, sine, cosine, tangent, or Pythagorean theorem. This will come up in very unique problems, and most likely stuff you might see in future years. All right. And that is all I want to go over today in this lesson. We will go over some more square root stuff on the next lesson, and definitely make sure you save these in these notes, or save these notes so you have them to use on a possible test question that might come soon. All right, thank you very much.